Okay, so we're going to start with 2.8, which is all about inverse functions. Okay, so this is best illustrated by two examples. So let's define a function just with domain 1, 2, 3, 4, where if I start with these x values, then f of x goes like this. So let's say, let's just do it by arrows. Say we're going to the set 5, 6, 7, 8. So 1 goes to 5. So that means f of 1 equals 5. Let's say 2 goes to 8. So f of 2 is 8. 3 goes to 6. So f of 3 equals 6. And 4 goes to 7. So f of 4 is equal to 7. So these are your y values. And you were to say, okay, what is the inverse? So the question is, what is the inverse function? Right now I haven't really defined it, but it's we're just going to do it by an example first. What is the inverse function? And the way we denote it is f and then a little -1 of x. Okay. What is the inverse function? Well, it's just a function that goes the other way. So f inverse would have domain 5, 6, 7, 8, and then it would have range 1, 2, 3, 4. And since 1 went to 5, 5 would go back to 1. So this is f inverse. We would have x values here, y values here. So f inverse of 5 would be 1. 6, well, 3 went to 6, so 6 goes back to 3. 6 goes back to 3. So f inverse of 6 is equal to 3. 2 went to 8, so 8 goes back to 2. So f inverse of 8 is equal to 2. And finally, 4 went to 7, so 7 goes back to 4. F inverse of 7 is equal to 4. So this would be the inverse function f inverse of x, where the original function f was given like so. So there's a couple of things to note. So notice here there are two properties that are happening, two things to observe. So one is that the domain of f is the range of f inverse. Right? The output values for f inverse were the domain of f, and the range of f was the domain of f inverse, because we swap. So that's one thing that happened. And the second thing that happened was, suppose you started with an x. So if you had x equals, say, 1, which is in the domain, this is in the domain of f, then f inverse of f of 1, well, what was f of 1? F of 1 was 5. So f inverse then would be applied to 5. What is f inverse of 5? Well, that went back to 1. So we have f inverse composed with f of 1 being 1. And this is going to be true for any x in the domain of f. You can check that f inverse of f for any x value is going to be x where x is in the domain of f, just like it happened for 1. 1 f of 1 was 5, and f inverse of 5 went back to 1. Okay. In a similar way, if x was in the domain of f inverse, so for example, if for example, if x was equal to, say, 6, what would f of f inverse of 6 be? Well, let's check. F inverse of 6 was 3. So this is f of 3. What was f of 3? F of 3 was 6. That's how we define it. Right? We're just going, it's like, think of it like a round trip flight. Wherever you start, you end up back there if you do the composition. So you have that f of f inverse of 6 is equal to 6, or in general, f of f inverse of x is equal to x, where for all x in the domain of f inverse. And this is these are actually going to be the defining properties of an inverse function. Okay, I kind of explicitly did it for this example. Now, before we go still to define everything a little bit more formally, the question arises, when can you find an inverse of a function? It's kind of an important thing because it turns out it's not always possible. So let me do just an example where it's not possible in using a very similar set of numbers. Say we have a domain of f being 1, 2, 3, 4. So these are our x values. And our possible y values are still 5, 6, 7, and 8. And let's say 1 goes to 5, 2 goes to 8. Let's say 3 also goes to 5, and 4 goes to 7. So f of 1 is 5, f of 2 is 8, f of 3 is also 5, and f of 4 is 7. This is a good function. This is nothing wrong with this function. Okay. The question is, can we find f inverse of x? Well, let's say we want to, well, what is our usual task here? We swap the domain and the range, 5, 6, 7, 8, and then put here. Well, here, by the way, we won't include 6 because technically the range is everything that actually gets hit. So 6 would not be here because 6 didn't get hit. 6 wasn't one of the output values. So when we swap, we only take the output values that were actually hit. So that includes 5, 8, and 7. So 5, 7, and 8 are the only numbers that I'm including in my domain here. But now, well, 7 goes to 4. So let's put 1, 2, 3, 4 here. 7 goes back to 4. 8 goes back to 2. But then for 5, well, there's kind of a problem, right? It's like a love triangle situation. We have 1 going to 5 and 3 going to 5. Where does 5 go? So f inverse of 5 is sort of unclear, or not really, not what we call in mathematics, not well defined. So essentially what happens is this function, because 2 input values went to the same output value, so for f here, we had 2 input values going to the same output. And that's what we don't want. We don't want that. If we want to find if we want to find an inverse function, we can't have that happen. So that motivates the following definition. So a function f of x is what's called one-to-one. shorthand just 1 dash 1, 1 to 1, if whenever we have two different x values in the domain, then the output values are also different. F of x1 is different from f of x2. And we can see here that if f is 1 to 1, then we can define f inverse of x. So, and we can see here that for this function f, right here, that we gave as an example where we couldn't find the inverse, this is not, let me write this in a different color. Here, f is not 1 to 1. Why is that? Well, we had two different x values. 1 is different from 3. Those were two different x values. But then the output values ended up being the same. Right? Our condition for being 1 to 1 is that whenever x is we have two different x values, then the corresponding y values are different. And here that's not the case. 1 is different than 3, but f of 1 equals 3. Whereas here for the first example, here this function is 1 to 1. Here f of x is 1 to 1 because for any two x values you go to different y values. So here different x values go to different y values. And that's why we were able to construct this inverse function. Okay, so let's keep going. We now want to return to functions that we're sort of more used to. So we're going to return to do two final examples. We're just going to check if things are 1 to 1 first. So for example, let's say f of x is equal to x squared. It's going to be example 1. And then the second example is f of x being x cubed. And then I'll leave you guys with a couple of exercises after that. So what we want to check is f of x 1 to 1 for each of these? Okay, well, let's look at the graph. Let's do this graphically. It turns out for a lot of these problems, it's a lot easier just to see it graphically. And that's x squared. Here we have the graph x cubed. Looks like this. Well, you can sort of see visually here, right? Here's an x value, say 1. Here's an x value, -1. Those are two different x values, but their output is the same. F of 1 is 1. F of -1 is also 1 here for this first example. Whereas over here, so this one, number 1 here, this is not 1 to 1, because for the x values of 1 and -1, those are two different x values. The outputs for both of them are +1. And so you can see that visually by the following procedure. If I drew a horizontal line, the fact that this horizontal line crossed the graph twice, so this line here, line crossed the graph more than once, indicates the fact that there is the same y value for multiple x values. So this was a particular x value, this was a particular x value, and the horizontal line crossing twice said they have the same y value, in this case +1. As compared to x cubed, so for x cubed, if I draw any horizontal line, it crosses the graph only once, which means I won't be able to find two x values with the same y value. So here, the fact that each horizontal line crosses the graph I'll just say not more than once, in this case exactly once, but basically it's just doesn't have, it should be not more than once. Here it's twice or more. So not more than once means it is 1 to 1. Okay, so x cubed is 1 to 1. We are going to be able to find an inverse of this function for x cubed, but we're not going to be able to do so for x squared globally. Okay, so in conclusion, f of x equals x squared is not 1 to 1, and f of x equals x cubed is 1 to 1. And the way we determine that is by what we call the horizontal line test. Horizontal line test. What does the horizontal line test say? A function f of x is 1 to 1 if any horizontal line in the xy plane crosses the graph at most once. Right? Sometimes it's possible that a particular horizontal line doesn't cross the graph at all, and we'll see that in the exercise that I leave you. So here, again, just to reiterate, the horizontal line crossed the graph twice, hence it's not 1 to 1. For here, any horizontal line crosses the graph only once. So I'll leave you here with just a couple of exercises. So check if the following are 1 to 1 or not, are 1 to 1 or not. And I'd suggest using the horizontal line test. So A, f of x equals the absolute value of x, and B, f of x equals 1 over x. Okay, so we'll begin the next video with those two examples.